Okay, so continuing our previous lecture, the calculation of the transfer functions, again, a s square y minus sx of 0, and this is the c. And if we will do the manipulation, we'll get all the x's on one side and the y's on one side. Then we divide the x divide by y, and then we'll find the transfer function. So if we assume that all the initial conditions are zeros, sx of 0, x of 0, all of these where I have the 0 can be equated to 0 at the initial condition. So this boils down to a s squared xs c s y of s minus b. And eventually, if we rearrange as we did in the previous lecture, we'll find x of s, we factor x of s out, then I'll have as squared plus bs equal cs y of s. And then if I divide x by y, then I will get cs divided by as squared plus b of s, which is equal to c divided by as plus b. So because here if I take s out, I have one function here. I can actually do it as note let me insert the equation here. cs divided by as square how do I do the square? Okay, let me do this. Isn't like that. I'll take here the s times c, and here I will have the s factored out, and then it's a S plus B, which is equal to, so we take the S out. So this becomes, again, I have to insert my final equation. This is C divided by ASB plus B. So that's where we got this ASB from here. That's why we said this is simple algebraic equation. I can do that because what do I do here? Want to increase the font a little bit. Okay. So that's where we got the C divided by AS plus B. And this is very simple algebra manipulation. If we were still to do it on the differentials, we would not have been able to do that. Okay, so that's actually what I have done. There I have it on this slide. And the S here, which I have it AS plus B, is the sigma plus J, the complex number omega. And omega is our frequency. So we transferred all of this from the time domain into the frequency domain in a linear manner. So going back to our function, we will write this function y bar t plus y of t equal u of t. So if I will do the transfer function for this one, which is an easy thing to do, so I will just take this. So this becomes the y bar s y of x, y of s, sorry, plus y of s equals u of s, and the transfer function g of s, let's do it here, g of s equals u of s divided by y of s. So this gives me, here before I do that, let me take this y of s, factor it out, which is s plus 1. So now, if I will do u of s divided by y of s, so this is u of s divided by y. So if I take, it's equal actually. 1 divided by s plus 1. So if I do the inverse in time domain, equals e to the power minus at, where my a is my constant a. In this case, it's 1. That's the a here. So this a to e to the minus at, which should be equal to, take this out, e to the power minus t. Because a is 1. Okay, this is more like it. So if I have another function where u of t and y of t are the input and output respectively of a system defined by the following ordinary differential equation, determine the transfer function and assume that there is no any energy stored, which means all initial values equal 0. So do I have the solution here? No. So let me make this as an exercise. Let me go back to my assignment for a second. I did this one. Okay. The man is given by So this I already done previously, so I'm not going to do this again. So you have, so this is the transfer function in general. This is my input, A0, Y, A1, Y, etc. And that's my equal the B's here, where X is the input of the system and Y, this X, that's my output, equal this input is the output. In general, the Laplace transform of the output divide the Laplace transform of the input, which is, we have done this equation right at the very beginning. This is the, again, simple representation. The B0 SM, B1 SM minus 1, etc., all the way to Bm minus 1 S plus Bm. So I'll take this function here and go to the beginning. It was here. That's the same one right here. Okay, so this is always, I have n equal or larger than m for my that's for my input, and that's for my output, and that's my that's the my output, sorry, the B's, and this is the input. So when the order of the equation, the order of the denominator, which is my, is greater, that's n, than the numerator polynomial, the transfer function is said to be proper. So that's called the proper equation when n, Sn, A0, A1, all of this is, which is the n is larger value than the m. It's called the proper. A proper function means the output will always show that part of the input is consumed and cannot expect the input source to continue to be increased after some time. Otherwise, it's called improper. That's one of the values of the characteristics of the Laplace transform. So if I have B0 S cubed plus 1 divided by A 0 S square minus S plus 1. Now the M here is a 3 because I will divide this by this one. So M equal 3, order of the numerator, and N equal to order of the denominator. This is improper equation. So now we can start something, and I will not continue it. I will just briefly. So once we have a transfer function, we should be able to deal with the stability of the system, if the system is stable or not, There are main objectives of the transfer function: define stability in time domain and the frequency domain characteristics of the system, and then the response of the system for any given input, how we can do that. These are the main objectives of having a transfer function. These find the stability of the system and get the time domain and frequency domain characteristics and see what the response of the system is. And the stability of, in general, for a network system. There are several meanings of stability: absolute stability, relative stability, marginal, could fluctuate between stable and unstable. So relative stability or instability, of course, the last one. Let's see what I have here, and I will stop. So this can be called control, or in fact, a network, any network system here. We divide again y, the output divide the input by x, and here is my B0 is m, and here is the n. So we have seen that if m is equal or larger than n, it's called proper. Otherwise, it's improper. So we find the roots of the denominator, which is the up here, and the what transfer function are called poles, the root of which are the B0s for the S here. These are called poles, and roots are values of S, where x of S, when we put x of S equals 0, then we solve the equation and we find the what we call them the poles. And there are something called zeros. The numerator, which is the B's here, are called the zeros. Roots are the values, so we find the poles and zeros of a function. These are the ones that give me the characteristics of my function. So poles of the system are represented by x, and the zeros of the system are represented by 0. So here, if I solve for my x and solve for y, so for x is my poles, and zeros are for my, and the y are for my zeros. And the system order is always equal to the number of poles of the transfer. So if my solution for x has 3 values, let's say +1, -1, -2, then it's called, the order is 3. We look at the poles. And here, this transfer function represents nth order plant, because here, if I have s to the n, and that's the y of s, which is my output here, y of s. We said the transfer function, our poles are represented of the x. So if I solve for x here, which has the x of s, this is multiplied by b0, sm, etc. So in this case, the nth order planet, the number of order, because I have n solutions, because s is raised to the power n. Here is an example. Y of s, s squared minus s S minus S square equal X of S. So you divide Y by X. This is Y divided by S, S minus 1. So we have to solve for this one here. So this is my G of S. And Y of S equals 1. Define my zeros here for Y of S. That's on the top is 1, so it's my zeros. There are no zeros. And the X of S, S of 1 minus S, so we define my poles, because here S equals 0 or S equal 1. So if I solve for this, so I say that my poles are equal to, and the system order equal to. So a number 0 is equal 0 because that's, so let's see, do I have an, I need to put one more. Okay, so let me adjust the assignment, the second assignment, and I will quit right here. Okay, so I'm stopping here. I will do here my next lecture. I'm going to be more. And I will put my next exam. Okay, for my screen. Put one more. Okay, so this is your assignment, guys. Save. All right, I will see you next Monday, please. Okay, stop share here and for all.